Hey guys, welcome back to the channel. If it's your first time here, my name is Aiden Potts and we go through math and physics tutorials as well as how to improve the mindset and learning skills of a student. In this video, we're going to be going through compound angle identities. And this is going to be one to maybe a three-part series related to these trigonometric identities. I think the big mistake that people make in learning identities is they just memorize the formulas. And the formulas that you can derive from, a basic set of like one or two formulas is actually really staggering. So to try and memorize like 16 or like whatever it ends up being, over 10 for sure, it's a lot more work than if you just learn the principles and can derive all of them from that. By the end of this video, you'll be able to take the compound angle identity of sine alpha plus beta, or a plus b, and be able to derive the rest of the compound angle identities, and there's 6 in total. If you guys like this content, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. So like I said before, we're going to be going through the compound angle identities in this video. And as you can see, there's a lot, and they look kind of complicated right now. Here we have sine of alpha plus beta, sine of alpha minus beta, cos of alpha plus beta, and cos of alpha minus beta, as well as tan of alpha plus beta and minus beta. So I'm going to go through this video on how to get from this angle identity right here, this sine of alpha plus beta, and how to derive all of them. And then you'll actually understand a little bit more deeply the relationships between a lot of these trigonometric functions. And that's way better than memorizing, because once you can work through this like 1 or 2 times, you'll actually end up memorizing them, but you're not going to be worried come test day if you forget them or what to do without a formula sheet, because you can just go from this one to the rest of the 6. So here there's an addition formula for sine. We have sine of alpha plus beta, and then a subtraction of alpha minus beta, and this is the same for all 3, sine, cos, and tan. We can also write 1 and 2, so equations 1 and 2 of the addition and subtraction like this. Sine of alpha plus or minus beta is equal to sine of alpha cos beta plus or minus cos alpha sine beta. And that's a little bit more compact of writing kind of both addition and subtraction formulas. So that might be helpful if you just want to memorize that. Similarly, we have the same thing for cos. We have an addition formula and a subtraction formula. In this situation though, you'll notice that the addition doesn't actually line up. Here it's subtraction. Whereas before we had sine of alpha plus beta, this plus matched this plus. So when we write it in a more compact way, we actually have to account for that. So we have to account for alpha plus or minus beta is equal to cos alpha cos beta minus plus sine alpha sine beta. So you see how that minus is first, and that's to account for this offsetting, like how this is negative and this ends up being positive. So what they're saying here, or what we're saying in writing a bit more compactly, is this plus corresponds to this minus, and this minus corresponds to this plus. And lastly, we have the tan. We have an addition formula for tan and a subtraction formula for tan. So this is tan alpha plus tan beta, and this plus corresponds to this plus. So when we write out the compact form, kind of including both the subtraction and addition formula, we'll have tan alpha plus beta, or plus minus beta, is equal to tan alpha plus or minus tan beta, because again, this plus here matches that plus, and this subtraction here matches that subtraction. But when we go to the denominator, we can see that we have a minus corresponding to this plus, so this one and that one, and we have this minus corresponding to this plus here. So again, similar to the cos identity, we'll have the tan identity to be plus or minus beta, so alpha plus or minus beta, tan of alpha plus minus tan beta, and 1 minus plus tan alpha tan beta. So that order actually does really matter. So I know I've been saying a lot of sine, cos, and tan, but I promise it will get easier. We're just going to kind of go through what the goal or the end result is going to be from this derivation. So here we have sine alpha plus minus beta. So these are all of the formulas we're going to need, kind of written more compactly, so we don't have to write out the addition and subtraction. And I'll show you how to get from the sine addition formula, so a plus b, to the rest of the formula. So now we can actually start deriving. So here we have sine alpha plus beta, and this derivation is done through geometry. There's a kind of a bunch of different ways to do it, but you're never really going to be asked how to get this in the first place. What you're going to be asked is, given one of these trigonometric identities, like this compound angle identity, solve the other ones. So this is where it's important, and we can go through in another video how to get this one particularly, but I'm going to go from this one and derive all the rest. So I'm first going to start with sine of alpha minus beta. This is going to be the result that we're going to get. So it's the subtraction compound angle formula. So here I'm going to write sine of alpha plus, but then I'm going to do in brackets minus beta. And the reason I do that is because now this will end up being sine of alpha minus beta. But now I can just plug in wherever I see a beta from this formula, so here and here, I can just plug in a negative beta, and that will result in the derivation kind of going forward. So if we're to write this one out, it'll be sine of alpha, nothing's changing there, then it'll be cos of negative beta, plus cos of alpha, and then times sine of negative beta. And this is the important step. So all we did was, instead of a positive beta, we put in a negative beta for that angle. And this is where we're going to need to remember our properties of even and odd functions. So an even function is flipped over the y-axis. It's symmetrical on the y-axis. So that means that if I put in a negative reflection, so this negative x squared, that'll end up being x squared. And so functions that are example would be a quadratic. So this quadratic is symmetric across this y-axis, so that would represent an even function. An odd function represents a reflection over the x and y-axis, and that will result in the exact graph that we had before. So an example of this would be negative x cubed. That's going to be the same as negative x cubed if we put a negative in front of that x. So an example of this would be the cubic function. So it looks something like this. If I were to flip it over the y-axis, it'll look like this. And then if I were to flip it over the x-axis as well, it'll end up equaling this. So with that review, we now know what even functions and odd functions represent. And we know that cos is an even function. It represents even symmetry, whereas sine represents odd symmetry. Now using this information, we can go through the rest of this derivation. So now, sine of alpha cos negative beta. So cos negative beta, since it's an even function, this will end up just being the same. This will end up just being cos of beta. Nothing changes in terms of the signs here because it follows this principle here. So next we have cos alpha multiplied by sine of negative beta. Well, sine of negative beta, we know that sine is odd, so this, if we put a negative in front of the x part here, or in front of like a reflection in the x-axis, or the y-axis, sorry, that'll cause a reflection in the y-axis. So we can actually take away this addition and put a subtraction that's going to account for this, this function here, because it's odd. So just like that, by just subbing in a negative beta into all the beta values, we get the subtraction formula for sine, which is the second compound angle identity. Now to get the third trigonometric identity, or the third compound angle identity of cos alpha plus beta, it's a little bit more involved, but all we need to know is cos, I'll do this in actually white, so cos of x is equal to sine of 90 minus x. So this is the complement property. So sine and cos are complements of each other, and the graphs will actually be shifted by 90 degrees, or pi over 2 if you're doing it in radians. Additionally, we can do it in the opposite way, so sine of x is equal to cos of 90 minus x. So this is an important property to note. It's similar to the even and odd functions that we were going over and their properties. It's going to be important to factor this into our derivation here. So now that I know that, I can say that our function here of cos of alpha plus beta, which is what we're trying to get, is going to equal sine of 90 minus, and then I'm going to put in this part of the angle, because realistically this alpha plus beta, that's just going to be an angle. So this is the complement angle, and this is what we're going to use to derive. Now that I've done that, I'm just going to distribute the negative here. So I'm going to do sine of 90, and now it'll be 90 minus alpha minus beta. Now this is kind of, I guess, a little bit of a tricky part, but we're going to use the previously derived sine, or the sine formula in subtraction, the compound subtraction formula. But now I'm going to group this, and I'm going to basically say that this green box here, this is A, and then it's minus this B. So it's kind of like alpha, this A is representing alpha usually, and this B is representing beta usually. So now I'm going to use this function here. I'm going to use this sine alpha minus beta, but I'm going to apply it to this A and this B that we now have. So I can still say that cos of alpha minus or plus beta is going to equal, and then I'm just going to use this part of the formula on this right side. So first, our first angle is sine, but it's really of 90 minus alpha, and then it'll be multiplied by cos of beta. Next it'll be minus cos of alpha, and remember alpha in this case is 90 minus alpha, because we're grouping those together, and then this will be times sine beta. So now that we have this form, we can again use the complements of sine and cos to simplify it. So it's cos of alpha plus beta is going to equal, well, sine of 90 minus alpha. If we scroll up, sine of 90 minus any angle is just going to be cos of that angle. So here we can say, instead of sine 90 minus alpha, we can say cos of alpha. And then cos of alpha times cos of beta minus, well, cos of 90 minus alpha, that's going to be sine of alpha. And then this will be sine of beta. And just like that, we've used this complement factor, or I guess property, and gotten our third compound angle identity. So now that we have our cos addition formula, we're going to try and get our cos subtraction formula. And this is very simple because we're going to use the same process we did for the sine from addition to subtraction. So now, instead of beta, I'm just going to put a negative beta in. So now I'll go cos of alpha plus, and then I'll do in brackets, negative beta is equal to cos of alpha, cos of negative beta minus sine of alpha, sine of negative beta. So now we can use our even and odd function properties to simplify. So this will just end up being cos of alpha minus beta. And this will equal, well, cos of alpha is going to stay the same, but cos of negative beta, again, since it's even, it has even symmetry, it's an even function, this will end up just being cos of beta. Nothing changes really, just that negative switches to a positive because it's symmetric across that y-axis. In this case though, sine of negative beta, well, if it's flipped over the y-axis, which it is right now, it also will be flipped over the x-axis, and that will have a symmetry of an odd function. So now it'll be, instead of this minus out here, it's actually going to be plus sine of alpha times sine of beta. And now we have our fourth compound angle identity. This is number 4. So now we're going to move on to tan, so the compound angle tan formula. So here we'll have tan of alpha plus beta, and we're going to figure out what that is equal to. Well, tan of any angle, and like the definition of tan, so if we do tan, if I scroll up and I'll just do tan of x, we know that is equal to sine of x over cos of x. So now I'll do sine of alpha plus beta over cos of alpha plus beta. And we already have like compound angle identities for each of these, for the numerator and the denominator. So again, we'll just fill that in given our previous knowledge. So the numerator will be sine of alpha cos beta plus sine of beta cos alpha. And it doesn't really matter which way or order these go. You could say cos alpha sine beta, but I'll keep it like that for now. And then in the denominator, it'll be cos alpha cos beta minus sine alpha sine beta. So now I'll do kind of a small trick, but it's really just dividing the entire equation by 1. But we're going to divide by cos alpha cos beta. And then cos alpha cos beta, because we can't change this. If we just divided by cos alpha cos beta, that would change the function. But we know that dividing it by this expression here is really just the same as dividing it by 1. So now, if I'm going to divide each of these terms, if we're dividing fractions, what we're doing is multiplying by the reciprocal, but in this case, the reciprocal is the exact same. So we're effectively just dividing out each term by cos alpha, cos beta. So each of these from cos alpha, cos beta. So if I scroll down a little bit, so it'll be sine of alpha, cos beta, divided by cos of alpha cos beta minus, and then this will be sine beta cos alpha divided by cos alpha cos beta. That's just the numerator. So it's kind of, you have to be a little organized here, but divide that, and now we're in the denominator. So this will be cos alpha cos beta divided by cos alpha cos beta, and finally sine alpha sine beta divided by cos alpha cos beta. So now that we have everything kind of divided by cos alpha cos beta, we can now see some cancellations happen. So here, cos beta over cos beta, that's just 1. And then sine alpha over cos alpha, I'll change colors now to make it a bit more clear. Sine theta over sine alpha over cos alpha is just tan of alpha. and then that would be subtracted by, well, again, we have this cancellation here. We have cos alpha in the numerator and denominator. So this will be sine beta over cos beta, which will just be tan beta. And then that will be divided by, here we're going to have cos alpha, cos alpha, cos beta, cos beta. So this is really just 1. And then now we're going to subtract by, oh sorry, this should be a plus here. I don't know why that's a plus. And this will be a plus as well. That was just a mistake there. So now it's be 1 minus sine alpha over cos alpha. So that's really tan alpha. But it's also multiplied by sine beta over cos beta. So this would be tan alpha, tan beta. So that is now our 5th compound angle identity. And that one's a little tricky, just like when we went from sine to cos. It had a bit more of an involved step. We had to account for the fact that the complement angles of sine and cos. And in this one we had to divide out by this cos alpha, cos beta. But now when we go to the subtraction formula, it's a lot easier. So now I'm going to rewrite, and this is the same for all of them to get to subtraction. Alpha plus negative beta. Again, I'm just going to put in a negative beta wherever I see beta. So now I have a negative beta in front of where my betas used to be. So this will be tan of alpha minus beta if we distribute that negative. And here we now have tan of alpha. And this is a good point to note that tan, just like sine, is an odd function. So it exhibits odd symmetry. So here, this tan, this reflection over the y-axis will be equal to a reflection over the x-axis. So it'll just be negative tan of beta. I guess I don't need the brackets. Divided by 1, and then again, this negative tan beta is going to create this to be negative, so a negative and a negative, this will be plus tan alpha tan beta. So that is the 6th and last compound angle identity. And I think you can appreciate that this is, even though this might take a little bit more effort up front, you'll actually end up remembering it for a longer time, and your retention rate will be increased, because it's a lot harder to just kind of rewrite these expressions over and over again and try and memorize it that way. Instead, you could just memorize one or have one angle identity and get the rest. And by doing this and getting the rest, I promise you, you'll have a much greater appreciation and understanding of the material at hand. Thanks a ton for watching this video. Like I said, this will be part of a multi-part series related to trig identities, and this is just going through compound angle identities. Next, we'll go through double angle identities, and then we'll go through Pythagorean theorem identities, and we'll pull it all together by going through a lot of example problems and giving you practice with these identities. If you guys like this content, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. I make a ton of content to help in math and physics, as well as improve the mindset and the learning skills of a student. Do you guys have any ideas of what videos you want me to do next? Let me know down in the comments below. Thanks again, and I'll see you guys in the next video.